Alright, time for another Jacobson video, and I just realized I probably should have called this playlist How to Basic Algebra. I think that would have gone over pretty well. Also, by the way, I'm like pretty proud of this line here is like not like if you look at the textbook it's like off on its own line, so I actually like pasted it in here separately and it actually like lines up pretty well. But anyways, I'm gonna stop focusing on that and let's actually focus on math. So we have this length function, and I will first prove that given a normal subgroup K in G, the length of G is equal to the length of K plus the length of G mod K. And this should make sense because this is going to use the previous exercise 3.3.2 a lot. And so you should sort of see like, oh, last time we proved that if we have a we can always find a composition series for G containing a particular normal subgroup K. And so it should make sense that if you have like a composition series for G, you could just think of it as like, oh, well, this is equivalent to a composition series which has a K in it, and then from there you have like that series going from 0 to up to K, and that itself is a composition series. And then you have the other composition series going from, well, when you go from K up to G, you can actually mod out by K and then get a composition series. But anyways, because you can basically split up a, because that's where this G mod K is going to come from. It's when you do that and you mod out by that normal subgroup. But anyways, that should give you the intuition that like, maybe these lengths should be the same. And by the way, something to note here, this is the number of composition factors, i.e. the number of graded pieces. So it's going to be one less than the number of actual subgroups, or the number of actual elements in your chain. And so that I actually lost a point on that for this exercise, I think, which is actually like, yeah, but hopefully I lost a point for that and not for something else, because if I did lose a point for something else, then some other part of this problem might be wrong. So that's a fun exercise for you, is to make sure that I haven't messed up anything in this. Actually, that should probably be an exercise for all of these videos. So, anyways, first, note that, and this is something that we need to state, that LG is well defined because by Jordan-Holder theorem, any two composition series for G are equivalent, and thus have the same, then I'm going to call this length. And when I say length here, what I mean is, well, like, oh, if you have two composition series, then the number of entries in each composition series is the same, but that turns into the number of graded pieces being the same, which here is what we mean by the technical term length. So when I say length here, it doesn't really matter if you use the technical definition or the like intuitive definition, but whatever it is, it's the same. Because that's part of what being equivalent means. So let's see here, they're the same lengths, and so the issue is like this function should not depend on your choice of composition series, and it doesn't, because if you choose any other one, it'll have the same length, and so the value will be the same. And so this is a well-defined function. So by 3.3.2, there is a composition series G equals G naught contains the way down to, let's say gk will be equal to k. Then this will go down all the way to gm, which is going to be equal to 1. Or I guess I wrote it as e. There's another problem that I've been working on lately where they just use 1. So, but anyways. So this is a composition series, and it contains k. So that's the thing. Not only that there's a composition series, but that it contains k. And that's what we know by 3.3.2. Then the length of G is equal to, well, how many entries are here? We have 0 through m, so we have m plus 1. But if you think about the number of graded pieces, that's going to be like the number of these normality triangles that we have here. And so that's actually going to be 1 less. So the length is actually just going to be m. So we have the length of G, and now we want to look at the lengths of k and G mod k. By 3.3.2, from k all the way down to e. Well, this isn't even by 3.3.2. This is just something that we state there. But it's obviously true because it's just what a normal tower is. But this is also a comp series. Well, it's a comp series for k. And so what is the length of k? The length of k is going to be how many of these things we have. And so what we have is k, remember k is equal to g sub k, lowercase k, but whatever. So let's see here. Is this going to be the right, is this going to give us the right number? So if we go from k through m, we will have m minus k. This is, and now, do I have to subtract 1 here? I'm trying to, I might. I think this is right. This is why I don't like combinatorics, because it shows you, like, how hard it is to count things. Oh, yes, it is right, because if we were to subtract k from every single index here, we'd be starting at 0, and we'd go up to m minus k. And then as by the argument we used here, we go from 0 to m minus k. The number of entries in there is m minus k plus 1, and then we subtract 1 from that to get the number of graded pieces, which will be m minus k plus 1 minus 1, which is just m minus k, and so this is the correct number. Alright, so I guess I can count some things, but not all things. Now by 3.3.2, and this we're actually going to refer to 3.3.2 because we don't want to have, this is something that you have to prove using isomorphism theorems, and I don't want to go through that again, and we don't have to because we proved it. We have a composition series G mod k equals G naught mod k, contains all the way down to gk mod k, which is of course just k mod k, and so this is just the identity. So this is a composition series for G mod k, and so the length of G mod k is, again, this, so we have these indices here from 0 to k, and so it's just going to be k. Then the length of G is equal to m, which, surprise, m minus k plus k, but this is just L of k plus L of g mod k as desired, right? Because that's what we wanted to prove. We wanted to prove that LG is equal to LK plus LG mod k. And this holds for any normal subgroup of G. And so now we want to prove that final equality, which I just hid from you because, I decided to mean here. There. So here H1 and H2 are both normal subgroups. And of course, my write-up, I used K's, so this is going to be a mess of notation. So for the final equality, first note that, is that thunder? I really hope not, because I was going to go for a run after this. First note that since H1 is normal in G, we have H1, H2 is a subgroup of G by the isomorphism theorems. I think this is the second one, but numberings tend to change from textbook to textbook, and so I don't want to have to rely on that. Although then again, this is from Jacobson, so I should probably use the numbering from Jacobson. But I don't know if my class used the same numbering as Jacobson, and I don't feel like going back and checking, so you can check. So not only is a subgroup, but in fact, since H2 is normal, these triangles are hard to draw as well, then for all G in G, G, K1, K2, G inverse, and I think that my class might have mixed up the inverses. Like, we tend to use G blank G inverse instead of Jacobson might use G inverse blank G, but it doesn't matter because it's a group. So this is obviously G K1 G inverse, G K2 G inverse. But by normality, this is just equal to, we bring the K1 and K2 all the way over to the right, and the stuff that's left over is G inverse, G inverse, which is just 1. So this is just K1, K2. So the product, K1 times K2, is normal in G. In fact, I think I proved this as an exercise. This might be one of the Jacobson exercises. But anyway, in any case, so now, by our favorite exercise, 3.3.2, K1, K2 has here, K1, K2 has a composition series. No, that's not what I need here. So K1, K2 is normal in G. Yeah, I don't think I need to have that K1 and K2, that the product K1 times K2 is normal in G. You know, I'm going to put in because I don't want to have to think about this on the fly. I'm going to put this part in parentheses so that it's not included if it's not necessary. I know that that's horrible. That's a horrible way to do this. But I'm just looking at what we're building up to in this particular paragraph that I'm on. Maybe I should start doing that in my write-up, like using actual paragraphs. Too much space. That means scrolling up more and more computer explosions. So let's see here. What we really want is we want K2 to be normal. Oh no, we do want this. Because so then K2 is normal in G implies K2 is normal in K1, K2. Oh, but wait, for this, well, this is obviously just because if G, K, G inverse is in K2 for all K in K2, then obviously this is going to hold, and for all G in capital G, then this is also going to hold for all G in K1, K2, which is, oh, why, I'm sorry, guys. I did exactly what I thought I was going to do at some point. I went to K's, and I should be doing H's. Sorry about that. So anyways, this is going to be so H1 times H2 is a subgroup of G by the isomorphism theorems. So then, since H2 is normal in G, then K2, it's definitely raining. I'm not happy about this. Anyways, since H2 is normal, well, I have an umbrella. Okay, so H2 is normal in G, and so then H2 is also normal in the product H1, H2. Because H1, H2 is a group by itself, and so this is well defined, and obviously it's just because H1, H2 is a subset of G, then it's this holds. Okay, so we have so now we have a normal subgroup of a composition series. So now, by our previous result, the length of H1, H2 is equal to the length of H2 plus the length of, let's see here, we take H1, H2, mod out by H2. Okay, so that's a useful fact. And now we have H1, H2 mod H2, and that should scream something at you. That should scream isomorphism theorems. Also, by the isomorphism theorems, K1, no, it's H's. I was doing so good on that. H1, H2 mod H2 is isomorphic to H1 mod H1 intersect H2. This tells us that the length of H1, H2 mod H2 must be equal to the length of H1 mod H1 intersect H2. as well as something else. Now what this says is, this says that H1, H2 mod H2 is isomorphic to this quotient here. And now this quotient on the right, this is H1 mod something. And since it's isomorphic to a group, this thing must be a group. And we know that like a group mod a subgroup is itself a group if and only if the thing we're modding out by is normal in the previous thing. More precisely, this implies that H1 intersect H2 is a normal subgroup of the product H1, H2. No. H1, because it's H1 mod this intersection. So the intersection is normal in H1. So let's see here. Let's see here. Now I have, since K1 is normal in G, well, that would be H1. So H1 has a composition series, and the length of this. Oh, right. So then, since H1 intersect H2 is normal in H1, we use our previous result. Stop. Okay. We use our previous result again, and we have that the length of H1 is equal to, and now we just apply the formula, but with H1 intersect H2 as our normal subgroup. We have H1 intersect H2 plus the length of H1 mod H1 intersect H2. But now this thing, okay, so this, i.e. the length of H1 mod H1 intersect H2 is equal to the length of H1 minus the length of H1 intersect H2. Thus, we now go to the length of H1, H2, and so now what is this? We know that we proved previously that this is length of H2 plus the length of H1, H2 mod H2. But now this is equal to the length of H2 plus, now we replace the second thing by H1 mod the intersection of H1 and H2. And so here, I'll make this look a little nicer. So H1, H, blah, blah, blah. And so we keep the H2, but now we just plug in our previous formula. And so this, we break up this quotient into the length of H1 minus the length of H1 intersect H2. Let's make this look even nicer. We'll do that thing where we put the computation on its own separate line. And this is as desired, because that should be precisely this equation here equals this guy. This should be precisely the equation that we were looking for, and let's see, H1, H2 equals H2. Okay, well let's flip these two. We get the H1 and the H2, doesn't matter, commutativity, and we subtract the intersection. Alright, so there we go. That completes our proof. And so I guess the reason you would think of this is you look at this H1 intersect H2 and you think, I know how to work with like the whole thing about composition series is that you have normal subgroups, just normality all over the place. And normality means that you can quotient, and quotients behave nicely. And so you might look at this h1 intersect h2, and that intersection there, that might give you the hint of, well, I remember there's that one isomorphism theorem where you take something mod an intersection, and this whole thing ends up being isomorphic to something else. And so that might make you think of doing either this h1 mod this intersection is isomorphic to h1 h2 mod h2, or maybe you might try doing this, like you might look at h2 mod intersect h1 h2. But either way, I think that's sort of how you would get started on this problem. So even though I didn't like come up with the solution myself, this sort of seems like not one of those algebra problems where you look at it and you're just like, I have no idea what to do, and then you still have no idea what to do, but then someone else comes along and they're just like, hey, if you do this if you do this and this and this, and you do these exact steps in the exact right way, without having any intuition as to why you would do these steps, then it'll work out. But I don't like those problems, and I don't think that this is one of them, because I think there are sort of hints in the problem statement as to how you get started and what sorts of ideas to use and what sorts of tools to use, mainly the isomorphism theorems. So anyways, there we go. We have completed this proof.